Good afternoon. And first of all, I would like to apologize for not being there in person. I had a problem with my agenda, and I was there yesterday. Unfortunately, it was not the correct day, but nevertheless, I had the opportunity to see many of the great presentations from yesterday. So today I have the pleasure to speak about radio science in experimental plasma physics in Portugal. And radio science is crucial in multiple aspects of the plasma physics. We use it for many different purposes. And I'm going to focus on three of our areas. One is how we are using it to nuclear fusion experiments. The other one is the use that we are giving to design spacecraft re-entry into atmospheres of different planets, and also how radio science enables us to develop new innovative materials. So in nuclear fusion, radio science is crucial in three different aspects. One of them is heating. We use radio frequency and microwaves to heat the plasma so that we achieve the temperatures required for to have nuclear fusion plasmas. The other one is to diagnose what is going on. And from diagnostics, we have some passive and some active diagnostics so that we understand and measure different parameters from the plasma. And this is crucial for us to understand the different aspects of the plasma physics so that we can optimize the experiments, because the final goal is to produce electricity. Why do we need diagnostics, which is one of the first areas where I'm going to focus? Because this is what we would know about the plasma without any diagnostics. So we would be completely blind to what was going on inside the device. So diagnostics are crucial to understand the different parameters, to understand what the physics is giving us, and what we could, how we can adapt and optimize our plasma. And one of the diagnostics that is more interesting for fusion is the microwave effectometry diagnostics. And the main reason is because it's non-intrusive. We can use it as a remote sensor that enable us to probe the plasma deeply. So we can penetrate the plasma and in the deep plasma measure some of the parameters. How does it work? So basically, we send a signal into the plasma. So it is a radar. We send a signal into the plasma, and according to with the frequency, it is reflected in a given density layer. So if we we measure the signal that is coming back. So we have the reflective wave as a phase shift that we measure. And with this, we are able, if we probe and if we sweep the frequencies, we are able to probe different radius of the plasma and enable us to do a density profile of our plasma inside the device. So this is quite good. So basically, we use a frequency modulated continuous wave technique. So we have a microwave generator. We have an antenna closer to the plasma. We inject the wave. We also have one of the signals that is used as reference signal. And the two signals are mixed. So we do a sweep, we mix the signals, and then we analyze the return signal, and we can retrieve and build the density profile. So one of the areas, or one machine where we have applied this, is the reflectometer at ASDEC subgrade, which is a fusion device operating in Germany. So here you have the scheme of ASDEC. So basically, what we have the possibility to probe the wave on the low field side, so on the outer boundary of our device, and on the high field side, so inside the device, and we can probe the plasma from both sides and retrieve the profiles from both sides using 4 different bands, microwave bands, from the K band up to the V band. And with these, we are able to measure deeply the density profiles. Just to give an idea, these are all the instrumentation that was designed and built at IST by IPFN engineers. And with these, we are able to retrieve, for instance, a density profile evolution. So in blue, you see what we call the L mode. And L modes means that we have a low confinement plasma. And you see that we have a profile from the outside to the inside, so the density is growing. But when we start heating the plasma, there's a transition to what we call the high confinement mode, and we start having density profiles very steep. And we are able to measure these profiles with the microwave reflectometry, and we are also able to measure the evolution of the profiles over time. So this is quite good. The problem is that when we are analyzing microwaves that we are injecting into the plasma, the propagation is quite complex. So we require full wave simulations just to understand some of the phenomena that are happening inside the plasma. So this graph is the result of one of our simulation codes. It's called RefMul, that was developed together with the Nancy University. And because the plasma is complex, non-homogeneous, non-stationary, and anisotropic, we have all these phenomena that ranges from multi-scattering local resonances. We have secondary cutoff, beam splitting, and wave trapping. And this requires a numerical full wave treatment. So this treatment and these simulations are crucial so that we understand what is going on with some of our more complex signals, but also very useful when we are designing a new diagnostic, because it allows us to start with to design what we call a synthetic diagnostic, that is to simulate what will be the response of the plasma to the wave we inject and simulate the signals that we can obtain. And by doing this, we are also able to optimize the antennas design and to start working on some of the algorithms to treat the signal. So developing a reflectometry diagnostic requires an integrated approach. Not only we have to understand microwave, physics, and engineering, we also have to work on the data processing. We have to work on numerical codes and synthetic diagnostics. So this is quite complex, and fusion devices are already very complex. So we need all these integrated approach to design microwave diagnostics for fusion. One example of the application, not only to measure density profiles, as I've shown you before, is to control the plasma position inside the device. Traditionally, we use magnetic probes, but magnetic probes are prone to suffer malfunctions when they are exposed to huge amounts of radiation. So microwave is one of the candidates to measure the plasma position. And the idea is that we are able to measure a given layer on the periphery. And by measuring the position of this layer, we are able to act into the plasma to control the plasma position. This is an idea that we tested also on ASDEC subgrade, first starting with the low field side measurements. And what you see there is the evolution over time of the density profile. And on the right, you see the signals, the reference signals, and then the control signal that was applying based on the data retrieved from the reflectometer. And later, we were able to do that using both the low field side and the high field side to improve the accuracy and to control in real time and replacing the magnetic diagnostics. Why this experiment was crucial? It was crucial because ITER, the International Thermonuclear Experimental Reactor, was considering using the plasma position reflectometer as one of the diagnostics for controlling the plasma, and we were strongly involved on that project. I don't have here all the details of the project, but I will just like to show you what some of the details of designing these diagnostics that seems trivial, but we had to take into account all the details. So what you see there is one of the bands that we had a very extreme band due to the space constraints, and we had to optimize these bands so that we didn't have any losses. And also because we are designing for a nuclear device, the materials are very, the type of materials that we can use are very restricted, which means that we need to test the options that we have available. And here we test one option with stainless steel waveguides covered with copper and with the band already performed. And in the end, we arrived to the conclusion that they work quite well. The band was perfectly optimized. It works this way. And also the coating on the stainless steel also worked well and according to the simulations. We had some problems here, but it was due to the manufacture process, and we had a lot of scratches on the coating. But nevertheless, it was a small step to a big diagnostics and very important diagnostics for ITER. Another example is the antennas will be in between big blankets that are in fusion devices are used to protect the vacuum vessel from the radiation. So the access that we have to the plasma is through a small antenna that looks into the plasma in between two big blankets. So here we had to simulate the effect of the blanket on the propagation. We had simulations from RefMul that I mentioned previously that was showing us that we could have some reflection problems. So we did this mock-up and we tested in a laboratory at IST and Koik chamber to analyze if we had effects. So when we think about designing diagnostics for fusion, all these small details matter and are quite important on the design. Unfortunately, ITER decided to cancel the diagnostic. It was a diagnostic I didn't mention, but we were also involved in the design with CIEMAT in Spain. So it was for us, it was not nice, but it was also not our fault. It was just due to schedule, the diagnostic was canceled. Nevertheless, we were already working on reflectometry for demo, which is the next step fusion device. And again, here the aim is to measure the density profile from the plasma and provide real-time feedback for the control with very high spatial and temporal resolution and high reliability. And here, because this is a device that aims at producing electricity, the amount of neutrons will be very high. There's a very big chance that, or a very big possibility that magnetics diagnostics will not work. So we need to have a very robust front end for microwaves with metallic antennas and waveguides withstand the high radiation and heat loads, and we don't have any sensitive parts. So just to give you an idea, the idea that we have is to have a big module that covers the full device, the device all around. And what you have here are the waveguides that are routed through the ports of the device. And we will have 80 pyramidal or antennas integrated in the blankets to measure the plasma in all these different positions so that we are able to control the plasma. And everything has to be active cooled, and everything has to be routed and optimized due to constraints, some very strong bands in some cases, and because we don't want a lot of noise. The other important aspect is that when we are designing these diagnostics, we also have to design for remote maintenance, which adds to the complexity of the design of the diagnostic. And this is just another of the problems that is not related to the radio science itself, but we really need to understand radio science to optimize our diagnostics. So what you see there is the effects of the radiation into the materials. So this is an ANSYS analysis, a thermomechanical analysis. And this is just to give you an example that the waveguides within the blankets will bend and will suffer deformations due to the temperature. So we need to check if these deformations impact on our signal and how it impacts on our signals. So again, one of the details that we had to take into account when designing for this type of diagnostics. There are many other challenges on designing microwave reflectometry diagnostics for fusion. I just give you an idea. There we have some articles published where you can look at, but you see how radio science joins very big science here. And we need to do a lot just to enable measurements in the plasma. Another aspect is the electronics that is to be adapted for our applications. And we are developing a compact reflectometer that allow us to reduce the space and to put all the electronics closer to the device. And the idea here is to have fast frequency sweeping of the radio frequency backend. And we are developing it using commercial monolithic microwave integrated circuits. So this is ongoing at IPFN. Antonio Silva here in the photo is developing this board, and we have already a prototype working. So soon we hope to install these in some fusion devices to test and some applications. Another area that I would like to mention to you is to use the use of reflectometry to study re-entry plasmas. The problem here is that when we have a spacecraft re-entering the atmosphere and we form the plasma near the surface, it's exactly, the profile is exactly the opposite of the profile that we have in fusion plasmas. We have the maximum density near the wall, and then it decays when we go further from the wall. So this adds complexity to the possibility of using reflectometry, because we have very steep profiles that we would not allow the wave to propagate. Nevertheless, we are doing some simulations, again using RefMul, to try to see if we find some areas and some frequencies where we can measure the plasma, so that we have some idea, experimental ideas of what is going on the re-entering plasmas. And the idea here is to probing the afterbody flows around the re-entry vehicle. But because in Lisbon we have this European shock tube for high enthalpy research, which is a shock tube that enables us to simulate re-entry atmospheres and the plasmas that form when we are re-entering on these atmospheres. So the idea is to use reflectometry here to probe the plasma. Actually, it's not a reflectometer. It will act as an interferometer. So the idea here is that we inject a microwave on one side, and we have the wave propagating. We have a front. What we do is we make a combustion on the combustion chamber. We break a diaphragm, and we have a shock wave propagating. So we want to probe the shock wave that is formed. And the idea is using interferometry, using the reflection on the other side of the vacuum vessel to retrieve the density, the line density from these shock waves. So this is ongoing activities. We still didn't do the measurements. We have already the devices. So this is the electronics built by Luis Cupido Technologies. Here, Luis Cupido was a researcher from IPFN, but has now his own company, and he built this W-band front end that we are going to use to measure the shock waves. Now, a different application that I would like to show you is our project to produce nanomaterials. We have a the Pegasus project, which is a production method which is very innovative and disruptive. It's a disruptive technology to produce graphene and graphene derivatives. We have already 3 patents and granted and 1 patent submitted. And the basic idea is that we use a plasma to disassemble different materials. Here we can use alcohol, for instance. And the idea is that when the plasma or the materials enter the plasma disassembles in the atomic components, and by controlling the reaction and the temperatures on the plasma, we are able to control the assembly or the reassembly of these atoms. And if everything is done properly, we are able to build graphene using that. And just to give you an idea, here we have our device. The plasma started with a waveguide surfatron-based setup, which is used to create a surface wave and induce the microwave plasma at atmospheric pressure conditions. So this is our industrial prototype. So that's where the radio science enters, is on the source that creates the plasma, and how we control the propagation of the waves in our chamber, so that we control the temperature of the plasma. So you can see here the industrial scale prototype, and you see inside the filters where we are collecting the graphene. Basically, what we have inside is graphene sheets being assembled. We can also have, changing the conditions of the reaction, we can have graphene platelets, or we can have nanodiamonds, or we can introduce some doping materials, and here you have some example with N-graphene dope, so graphene doped with nitrogen and metal oxides. So with this device and controlling the whole discharge, we are able to produce several different materials. So just to give you an idea, it's really pure graphene that we are producing. This is one of our samples. The big one is 500 milligrams. And just for comparison, here we have here a commercial sample, which we, in the end and after analysis, realized it's not graphene, it's oxide graphene, but is sold on the market for 1,200 euros per gram. So, so that's why our device is a very nice device. It produces high quality graphene derivatives that do not exist in the market, and we are now trying to progress further on the commercialization and optimization of this device. Another important aspect where radio science enters is on the properties of the material that we are producing. What we have here is we made a small disc with N graphene, so that is graphene compacted, graphene with doped with nitrogen that was compacted, and we did the analysis of how microwaves, and you have here microstrips, how they propagate through this material. And in the end, we realized that we have a material that has a negative dielectric permittivity. And this is quite good. Our interpretation is that we have plasmons appearing on the material, but we think that this material that we are just starting to test has enormous potential in many applications, for example, for electromagnetic shielding, for cloaking plasmonic antenna satellites, military and aerospace applications, and we are looking to develop it further. So here, radio science is more on the side of what properties are enabled by the material that we are producing in our devices. So in the end, radio science for us is an enabler of many progresses on plasma science, and has been key in some of the IPFN applications and developments. There are some other developments that we have related. I selected those three. So thank you very much for your attention. Unfortunately, I will not be there for answering your questions, but please feel free to contact me, and I will be very pleased to answer you or to discuss potential collaborations in the future. Thank you very much.